Okay, class. So this video is for the lecture that we missed on Friday. We're going to learn about limits from the right. So limits are what this class is all about. They let us do everything that we're going to do. But let me remind you what we did last time. So last time we saw that the average rate of change of a function from one x value to another looks very much like the slope of a line. It is the slope of the line between the 2 points that are on that graph of that function. Okay, so that's what we saw last time. It measures the average amount of output change versus input change. We want to go from average to instantaneous. And to do that, we need these things called limits. So we're going to spend a couple weeks learning about limits. Okay, so just to sort of hint at the idea of how limits work, let's think about an interesting problem where we calculate average rate of change a couple times for the same function. So it's going to be x squared, just to start with something not so difficult. And remember, it looks like this. It's a little parabola. So let's figure out the average rate of change from 1 to 4 first. So that would be, oops, sorry, my pen is not working now. Okay, there it goes. Nope. Okay, so that would be 4 squared minus 1 squared, just using the formula very quickly, because we practiced it already so much. Skipping some steps. It's this, 4x squared, and then we get 15 over 3 is 5. Okay, so on average, from 1 to 4, you're going up by 5 on average. But if I change it from 1 to 3, so I move this second number a little bit closer here, well, then the average is going to be different. So it would be 3 squared minus 1 squared over 3 minus 1 is 8 over 2 is 4. So it's not the same anymore. It's a little bit less. So the idea is to keep bringing the second number closer to the first number. So next I could go from 1 to 2, and then I get 2 squared minus 1 squared over 2 minus 1. So I get 3 over 1 is 3. Then I could go even closer. I could go from 1 to 1.5. And that one probably need a calculator to do real quick, but it's doable. It turns out to be 2.5. So the idea is that we're getting average rates of change as we move the second point closer to the first point. And what's that supposed to be doing? Well, conceptually, the idea is that if we move x to infinitely close, whatever that means, that's what we need to learn about with limits, to x1, then these averages, the average rates of change should go toward instantaneous rate of change. Sorry, my pen is not cooperating. It's been a while since I did this video stuff. Should go towards the instantaneous rate of change right at x1 instead of from x1 to some other number. So like calculating the exact speed that your car is going at one moment in time instead of averaging from the beginning of your trip to the end of your trip. Okay, so that's why we got to learn about limits. That's what limits will help us do. Okay, is figure out how to find instantaneous rate of change at a specific number instead of from one number to another. All right, so we're going to learn about limits. Okay, we're just going to jump into an example to see how they work, sort of. It sort of seems a little bit, I don't know, silly right now to do this. We don't really seem to do much, but later on we will do more things. Okay, so the idea is this. We can take a function and plug in x values approaching 3, whatever that means, from the right. Now there is a deep and like very very precise definition of this stuff, but we're just gonna sort of be a little bit loose with it. And so what do I mean by approaching? Well, you just pick numbers that are going towards 3. I don't know, like 5, 4, 3.5, 3.1, 3.01. So you get closer and closer and closer, but from the right, not from the left. Then we could see what the function does. 12, 10, 9, 8.2, 8.02. And the idea is that as you plug in values to the right of 3, which we write like this, as x goes to 3 with a little plus sign up there. So here, x values go toward 3 from the right. As this happens, the function, what are the y values doing? They're going, well, it just sort of eyeball it at this point. They go towards 8. Okay, so the y values go toward 8. Now we could visualize this with a graph, of course. So here's 3. Here are the numbers that we plugged in, 4 and 5. And here's 8. So you end up with 12, 10, 9, and then these smaller numbers here. So you can see that as the x values go this way, the y values go this way towards 8. Okay, I'm not going to graph it nicely. It's not going to come out nice. But and of course, the actual graph of this function, this is just a line that happens to actually hit 3, 8. Which is not a coincidence, and it is related to the limit. But right now we just want to think about limits. We don't want to think about actually plugging in 3. We want to think about this kind of concept here. Okay, so then we'll see why later we need to do this, but for now it seems kind of silly because you could just say like, well, the limit is just what happens when you plug in the number. Okay, but don't think about that. Don't think about it like that yet. All right. So formally, we say something like this. The limit of f of x as x approaches 3 from the right. So that is just a longer way of saying this thing that I wrote here, x arrow 3 with a positive sign on it, is 8. Okay, so then the is 8 is really hiding all of this notation that I wrote before. F of x goes to 8 with the little arrow. Okay, and the way we write this, because math people always like to have notation to say things very quickly and confusingly. So we write this as Oh, it's horrible. Okay. Limit. I have to take a pause. Give me 1 second. Okay, I got myself a horrible tasting cough drop and I'm ready to go. Okay. So where was I? We write this as limit as x goes to 3 with a little arrow. The plus, that's just saying all of this stuff. But of f of x, that's what goes here, whatever you're taking the limit of. You should think of the limit as something you apply to a function. You take the limit of the function as the x approaches a number. And then whatever it is, you write equals 8. Okay, so that's where this is going there. Or since we have a particular function in mind, we could just write that function here, which it was like 2x plus 2, and say that that's 8. Okay, so we're just going to practice doing this kind of thing. So you'll be asked to find limits. Now, later on, you'll find limits in much faster ways. But right now, it's really just eyeballing it sort of by plugging in numbers. So if I say this, I'm asking you, what's the limit of the function x squared plus 1? So here, this is the function. So what happens when I plug in numbers to x squared plus 1 that are to the right of 2 and go toward 2? Okay, so you start with 4, you get like, what's that, 16 plus 1 is 17. 3 squared is 9, plus 1 is 10. The first ones, they don't really tell you much. It's not until you get to the very close to 2 that you can sort of guess where it's going. So I don't have a calculator, but you can plug these in yourself, and you're going to see that it's going to go towards 5. Okay, so this little chart just tells you the answer, which is that the limit as x goes to 2 from the right, that's what all that says, of x squared plus 1 is 5. Now, of course, if you just plug 2 into the function, you also get 5, but that is merely a coincidence that will not always happen in the future, so don't just do that all the time. They're not always the same. Okay, it's just a coincidence in this case because we're picking very simple problems. All right. So let's see an example where this doesn't happen. Okay, so if I ask you to find this limit, x goes to 3 from the right, of x minus 3 over x squared minus 9. Now if you plug in 3, so here the function we're looking at is x minus 3 over x squared minus 9. If you actually try to plug 3 in, you get 0 over 0, which is, of course, not defined. So that's not an answer. But the limit can still exist, okay? So that's the interesting part about limits, is even when there's a number that you can't plug in, so you can't actually say, like, what happens when I plug in 3 here to this function? What happens? It's undefined. Even though you can't plug 3 in, you can still do this. You could say, what is the limit as x goes to 3? And so we'll just make our little chart again. And if you have a calculator handy, it'll be easier for you to just do it yourself. I'll just give you numbers you could try plugging in. This one is kind of hard to see what it's going towards. But as you plug this in, this will go towards 1 over 6. We'll figure out ways to do this much more simply later. So don't worry so much about where I got that 1 over 6 from in this case. Right now, what you need to know is just how to interpret this information, which is to say, like, okay, this means that the limit as x goes to 3 from the right. So as you plug in x values going towards 3 from the right-hand side, this function that we have here, although we cannot plug 3 directly into it, we can say that the values go towards 1/6. Okay, plugging in 3 does not give you 1/6, but the values get closer and closer to 1/6 as you plug in numbers closer to 3. Okay, that's what this says. Okay, so we're going to get a little bit more formal because the word approach is still not precise enough, I guess. Because I'm just sort of saying like, go towards 3, go towards a number, see what happens. The more precise definition is as follows. For limits, goes like this. The limit of a function as x approaches a number c from the right. So again, the word approaches is not precise, but we're using it. Just think of it as goes towards little x values marching towards the number c from the right. Okay, so visually, the idea is here's your number c, and x is just going along towards c in that direction. Okay, so the limit of fx, the function as x approaches a number c from the right, is another number, L. So that's going to be what the y values are going towards. Okay, so the y values of the function will be going towards this number L. And it's written using this notation. So before I had chosen specific numbers, now I'm leaving it as C. Okay, that's the limit, but what does it mean to be the limit? If it's sort of a game you have to play. If you can always defeat me in the following game. Okay, so this is really what it means for f of x to go towards L, for the limit to be L. Okay, here's how the game goes. No matter how close a number, I'll call it y, that I pick to L, so it's a number close to L, you can pick a number to the right of C that when you plug it in, to f of x, it makes f of x closer to L than the y that I picked originally. Okay, so it seems very, very convoluted. But this actually corresponds to an even more fancy definition called the epsilon delta definition of the limit, but I turned it into a game to try to make it easier. So it seems confusing, but we just got to use it just to see how it works. So for example, let's think about a limit that we already did and use this definition to say y is the limit as x goes to 5. Sorry, 5, 3. Yeah, let me just erase. Okay, y is the limit as x goes to 3 from the right of 2x plus 2. Y is this 8. Okay. According to this more abstract idea, this game that you have to play. Okay, so first let's identify everything. So here C is 3 and L is 8 in this notation here, right? So the idea is I have to pick a number. So let's say I'll pick 8.5. All right, it's going to be close to L, the supposed correct limit. Okay. So you have to pick an X value. So something close to C. So you're always picking X values that are getting closer to C. And what they do is when you plug them in, I sort of created this limit here, not limit, I don't want to use that word because we're already using it, sort of like this border that you can't surpass. Okay, so I say 8.5, you'll never get closer to L, which is 8 in this case, than 8.5. And you say, well, all I have to do is pick something very close to the number C, which in this case is 3, and plug it in, and then you will beat me. You will get closer to 8 than 8.5. Okay, so how about you pick, I don't know, 6. No, sorry, not 6. That's too far probably. Let's pick how about 3.25. Okay, so you pick a number. Let me draw a new picture here because that one's getting messy over there. So here's the supposed L. And I said, you cannot get closer than 8.5. I bet no matter what you do, you cannot get closer than 8.5. But you pick 3.5. Okay. And then when you plug that in, you get, let's see what's that, 7. Oh, sorry, 3.25, not 3.5. What is that? 7, nope, 6.5 plus 2. Oh, it's right on 8.5. Well, what that means is you just got to pick something even closer. So how about like 3.01? So let's try 3.01. Okay, so if I plug in 3.01, I'll get 6.02 plus 2 is 8.02. Okay, so that did get you closer because 8.02 is down here. Okay, so you plug that in and you got yourself closer to L than I did. Okay, so what makes 8 be the limit is that no matter what I started with, you can always defeat me. Okay, so you defeated me once. You beat me once, but 8 is the limit because you can always beat me. And proving it is much harder. So you'll learn that in a much later math class if you decide to be a math major. But for us, this is just going to be good enough. So it's because you can always beat me, but you're not going to have to prove that you can always beat me. But for example, if I picked like 8.0001 as my boundary to say like you can't get any closer than me again, now I'm down here, 8.0001, you could still beat me. You just have to go even closer to 3. You just have to go like 3.000001. Then when you plug that in, you will still be closer to 8 than I was. Okay, so no matter what I pick, as close as I get to 8, you can always pick something close to 3 that beats the thing I said you couldn't surpass. Okay, so it's very abstract. We're not going to use this too much, luckily, unless you go into becoming a math major and you do real analysis, then you'll learn what this actually is doing. Okay. Let's also see something that's wrong. So if I ask you, what's the limit as x goes to 2 from the right of x squared, and I say it's 5, this is wrong because that definition doesn't work. Okay, so here, c is 2, L is 5, f of x is x squared. If I pick a number like 5.5 for my y, you can't ever beat me like you could in the previous game. Okay, so that tells you that 5 is wrong because I picked something close to 5. You are unable to defeat me and get closer to 5 than I am. The correct answer is actually 4, but again, we're not going to worry about that. Okay, so just other examples of this kind of stuff is just doing the same thing. So I'll just tell you the correct limit of something. So something like this. Okay, the correct limit is 6. And all I want you to do is try to defeat me at this game. Okay, so the idea is this function is pretty complicated, but we can still sort of visualize what's going on. 8 is the number c here. 6 is the correct limit. And I picked y equals 7 for the thing that you cannot get past. So you got to pick something over here, pretty close to 8, so that when you plug it in, it gets you under this line, basically closer to 6 than 7 is. So you just, try out different things. So you could try something close to 8 is 9 and see if that works. If I plug in 9 to this function here, I get 1 over square root of 10 minus 3, which again, you need a calculator to figure that out. It might be closer to 6. It might not be, but just try it out. Okay. Yeah, I just want you to get closer. And the one way to cheat is to just go really, really close. So if you just pick like 8.000001, then for sure you are going to be very, very close to this L, and therefore you are going to defeat me at the game because you're going to be much closer than my boundary. But the point is, like, even if I went really, really close to like 6.000001, you could still beat me by going even smaller. Okay, another one. This is, sorry, no, 4. Limit as x goes to 4 of x squared minus 16 over x minus 4 is 8. Okay, so here c is 4, L is 8. Defeat me if I pick something like 9. Okay, so again, visually, here's c. The limit is 8. I'm picking a boundary of 9 and saying that you need to defeat me by picking something over here so that when you plug it in, you are closer to me, or closer to 8 than 9 is. So you could try 5 if you just want a nice whole number, but it might not be close enough. So you get 25 minus 16 over 1 is exactly 9, so it doesn't beat me, so you got to get a little bit closer. So like 4.5 would probably do it. Okay, so just figure out what that is, and then if it's closer to 8 than 9 is, then you've successfully defeated me at this game. Okay, so I just want to stress that the reason that 8 is the limit is because you can always beat me at this game. Once again, not just because you could beat me once when I pick 9, but because no matter how close I go, you can always beat me by going even closer to 4 and getting you past that boundary. Okay, so for now, this is what limits are about. But later on, we're going to learn ways to calculate limits without just like drawing fun pictures and guessing sort of, and use more algebraic methods. Okay, so that's it for this video. See you guys hopefully in person on Monday. I'm not sick anymore. That's all.